Hello again, this is the Pencrest High School AP Physics 1 video series. This is video 9A, Introduction to Electrostatics. Now, sooner or later in just about every science course, there's some reference made to atomic structure. So, most of us are familiar at this point with what's called the Bohr model of the atom. In this model, the nucleus in the center is composed of protons and neutrons. You see it here. And the electrons orbit the nucleus as shown. This model is simplified, but it will serve our purposes. If we could see an actual atom of this size, the nucleus would actually be much smaller. In reality, the analogy that's usually given is if the atom were the size of a football stadium, the nucleus would be a gumdrop on the 50-yard line. So again, if at these scales, it serves our purposes to show what the nucleus more or less looks like. That's not really to scale. Now, protons are relatively massive and have what's called a positive charge. Neutrons are just about the same mass as a proton, but are electrically neutral. They have no charge. Electrons are much less massive. They're about 2,000 times less massive than protons, and they have what's called a negative charge. The charge on the proton and the charge on the electron are of the same magnitude. They are opposites in the sense that there are two types of charge, and one is positive and one is negative. Now, the negative charge on the electron and the positive charge on the proton are what it's called the elemental charge. It's impossible to isolate a charge that is smaller than this value. On the formula sheet, this is called electron charge magnitude. It's abbreviated with a lowercase e. Its magnitude is 1.602 times 10 to the minus 19 coulombs. The capital C is for coulombs, the unit of charge. We'll get to that shortly. But again, this is the smallest possible unit of charge. You can't have a single charged object that has a charge less than this much. Now, again, the decision to call the proton charge positive and the electron charge negative is arbitrary. It can be considered a sign convention like right, left, up, down, clockwise, counterclockwise. Again, plus and minus is the easiest way to differentiate one from the other. There are two types of charge. We could just as well call them up and down, or left and right, or black and white, or whatever you want. There are two different types of charge, the proton charge and the electron charge. Arbitrarily, the proton was called positive, the electron was called negative. Doesn't really matter why. Now, in order to give an object a charge, we either add or remove electrons from it. Electrons, as you can see, sort of orbit around the nucleus in these differently shaped orbits. Electrons are much easier to remove from an atom than protons are. In order to remove protons and move a positive charge, we would have to break apart the nucleus, which involves atomic or nuclear physics, and it's beyond the scope of the course. Stripping or moving electrons from an atom is relatively much easier. If we add electrons to an object, the charge on the object becomes negative. If we remove electrons, we are subtracting a negative, and the charge on the object would then be positive. So adding electrons makes a negative charge, removing electrons makes a positive charge. An object is said to have a net negative electric charge if it has an excess of electrons. So an excess means it has more electrons than it has protons. It's said to have a net positive electric charge if it has a deficit of electrons. So it has fewer electrons than protons. We would not say that it has more protons, because that implies that the positive charges have been added. Again, it's been the subtraction of the negative that makes the net charge positive. Electrically neutral objects have the same number of electrons and protons, which makes sense. Now, the unit of charge, charge is measured in coulombs. It's named after Charles de Coulomb. We'll get to Coulomb's law a little later on. Has the abbreviation capital C. Most static electric charges are measured in microcoulombs. A microcoulomb, this metric prefix mu, indicates 1/millionth or 10 to the minus 6 coulombs. So a coulomb of charge is, at least in everyday experience, a very large amount of charge. The kind of static charge that you get from a doorknob or something, especially in the wintertime when the air is dry, that's about 10, 15 microcoulombs. So a coulomb of charge is a great amount of charge. Now we're going to talk a little bit about the conservation of charge. We already know that conservation means that something stays the same or stays constant. In an isolated system, the total charge is conserved. The charges can move between objects in the system, but the total amount of charge remains constant. In the event that charges move between objects in the system, again, it's the negative charges that are transferred from one object to the other, not the positive charges. In a system where charged objects are touched together, or there's a conducting wire placed between the objects, there's some way for electric charges to move back and forth. The net charge in the system will distribute itself evenly so that it's divided evenly among the objects in question. So here's an example. We have a charged object, Q1, that has some charge plus 6Q on it, and another charged object, Q2, of charge negative 4Q. When the objects are touched together, we want to know what's going to happen. So what we see is that the net charge on this system is plus 6Q minus 4Q. We add these together and we get plus 2Q. This is the net charge on the system. When we touch the objects together, this net charge is going to evenly distribute itself over the two objects. So we have two objects here. We have a charge of plus 2Q on the system. That means each of the objects will have a charge of plus Q after they're touched together. So in order for this to take place, the Q1, the 6Q, has to be changed from a plus 6Q to a plus Q, which means it is receiving a charge of negative 5Q. So it starts at 6Q, minus 5Q, ends at plus Q. The other object starts at negative 4Q and has to go to plus Q. Now your initial inclination might be to say that it receives a positive charge of 5Q, but again, it's the negative charges that move, and that means that in order for the charge to go from negative 4Q to plus Q, it must have lost negative 5Q. So again, we're subtracting minus 5Q, which makes the net on the second object go from minus 4Q to plus Q. So in other words, negative 5Q is transferred from this object to this object, and we end up with a plus Q on each one. Okay, so again, it's the negative charges that move, but the total charge in the system before and after remains the same. Okay, that's introduction and conservation of charge. Next up is Coulomb's law and the interactions between charged particles. Until then, enjoy, and I'll see you again soon.